Welcome to this guide to interpreting carbon-13 NMR spectra. My name is Michael Edmonds and I teach chemistry at Christchurch Polytechnic Institute of Technology in Christchurch, New Zealand. This video has been developed as a resource for Achievement Standard 3.3 of the NCA curriculum in New Zealand. However, it can also be used by anyone as a generic guide to carbon-13 NMR interpretation. Carbon-13 nuclear magnetic resonance, or carbon-13 NMR for short, is an important analytical technique used by chemists to help work out the chemical structure of organic compounds. It provides us with two key pieces of information about an organic compound. First, it can tell us how the carbon backbone is arranged, and it can also tell us what functional groups are present, particularly when used alongside other techniques such as infrared spectroscopy and mass spectrometry. So let us begin by looking at an example of a carbon-13 NMR spectrum. Here we have the spectrum for 2-pentanone. 2-pentanone contains 5 carbon atoms, each in what we describe as a different chemical environment. Consequently, the spectrum contains 5 peaks, one for each carbon atom. The x-axis of the spectrum is a measure of the different chemical environments of each carbon atom and is referred to as the chemical shift. It is measured in parts per million, or ppm. When describing the relative positions of peaks, those appearing to the left-hand side of the spectrum are referred to as downfield, while those on the right-hand side are referred to as upfield. So now let's identify which peak belongs to which carbon atom in 2-pentanone. On the right-hand side of the spectrum, the peak furthest upfield belongs to the CH3 group marked in green. CH3 groups attached to a CH2 tend to appear around 15 parts per million. Moving slightly downfield, we find the adjacent CH2 shown in blue. The chemical environment of this group, i.e. between a CH2 and a CH3, puts it in this area of the spectrum between approximately 15 to 25 parts per million. The next CH2 group, however, is significantly further downfield. This is because it is adjacent to a carbonyl group, which pulls its chemical shift downfield. The carbonyl carbon atom appears far downfield. Most carbonyl atoms appear between 160 and 220 parts per million. The CH3 group on the left-hand side of the 2-pentanone molecule, shown here in pink, appears just under 30 parts per million. It is the influence of the adjacent carbonyl group which pulls this group further downfield than the CH3 group on the other end of the 2-pentanone molecule. So we have now matched each peak in the carbon-13 NMR spectrum with the corresponding atom in 2-pentanone. In order to be able to do the same with other different carbon-13 NMR spectra, we need to learn some general rules and patterns for carbon-13 NMR interpretation. This table outlines where different types of carbon atoms appear on a carbon-13 NMR spectrum. Carbon atoms in simple alkanes or in alkyl chains appear at the upfield end of a spectrum. As a general rule, CH3 groups are slightly further upfield than a CH2 group in a similar environment. Carbon groups attached by a single bond to atoms such as chlorine, bromine, oxygen or nitrogen are found in the region between 35 and 100 parts per million. The carbon atoms of an alkene group appear between 100 and 150 parts per million, while those in carbonyl groups occur closer to 200 parts per million. Moving on to another example, let us use what we have learnt from this table to identify the peaks in hexane. We will also use this example to see what effect symmetry in a molecule has on the number of peaks appearing in the carbon-13 NMR spectrum. Hexane contains 6 carbon atoms, however its carbon-13 NMR spectrum has only 3 peaks. Why is this? Hexane is a symmetrical molecule, as indicated by this red line of symmetry. Consequently, the CH3 groups at either end of the molecule occupy chemically equivalent environments. So do the adjacent CH2 groups, and so do the 2 central CH2 groups. Consequently, this explains why there are only 3 peaks in the carbon-13 NMR spectrum of hexane. With regards to the relative chemical shifts, we see that the CH3 groups occur upfield from the CH2 groups. This is typical for organic compounds. Linear alkanes such as hexane, which contain an even number of carbon atoms, will have half as many peaks as there are carbon atoms. So what do you think will happen with the linear alkane such as pentane, which contains an odd number of carbon atoms? How many peaks will we see in the carbon-13 NMR spectrum of pentane? You might like to pause the video now to think about the answer to this question. In a linear alkane containing an odd number of carbon atoms, the plane of symmetry runs through the central carbon atom. Therefore, the number of carbon-13 peaks can be worked out by dividing the number of carbon atoms by 2 and then by rounding up to the nearest whole number. For example, in the case of pentane, 5 divided by 2 equals 2.5, which rounds up to 3. The carbon-13 NMR spectrum for pentane has 3 peaks. Again, notice that the CH3 groups are upfield from the CH2 groups. Before we move on to other organic groups, here is a question for you. For the octane molecule shown above, how many different carbon environments are there, and therefore how many peaks would you expect to see in the octane carbon-13 NMR spectrum? Pause this video to give yourself time to answer. If you answered 4, then well done, you are correct. As you can see, the line of symmetry divides the molecule into 2 identical sections, affording only 4 different chemical environments. Let's now move on to look at the effects branched alkanes can have on symmetry. How many peaks would you expect to see in the carbon-13 NMR of the following compounds? Stop the video now and see if you can work it out. In this first example, that of 3,4-diethylhexane, we can identify 2 lines of symmetry which cross in the center of the molecule. Consequently, there are only 3 different carbon environments in this molecule, and there will only be 3 peaks on the carbon-13 NMR spectrum of this compound. In the second example, that of 2,2-dimethylbutane, we can identify a line of symmetry shown in red. There are only 4 different carbon environments in this molecule due to the symmetry around the line shown in red. By rotating the carbon bond between the green and the yellow carbon atoms, all of the blue methyl groups are indistinguishable from each other. Looking at the chemical shifts in 2,2-dimethylbutane, we see, as expected, the carbon of the CH2 group is furthest downfield, while the carbons of the CH3 groups are upfield, with the CH3 carbon adjacent to the CH2 group being furthest upfield. Looking at our final example, that of 2-methyl-5-ethylheptane, we can identify 2 separate lines of symmetry which create chemically equivalent environments. Consequently, there are only 7 different carbon environments in this 10-carbon molecule. Now that we have seen how chemical equivalence occurs in alkanes, let us examine how the presence of a single substituent, or X group, where X equals chlorine, bromine, hydroxyl or amine groups, can affect both the chemical shift and the symmetry of an organic molecule. In this first example, we can see by placing a new functional group, for example chlorine, at the end of an unbranched alkane, symmetry is removed. For example, in 1-chloropentane, by placing chlorine at the end of the carbon chain, none of the carbon atoms are now chemically equivalent. If we now look at the carbon-13 NMR spectrum of 1-chloropentane, we can see the effect that the chlorine substituent has on the chemical shift. The carbon atom closest to the chlorine atom is shifted the furthest downfield, and as we move along the carbon chain away from the chlorine atom, the chemical shift moves upfield, with the CH3 furthest to the right-hand side of the spectrum, i.e. the furthest upfield. If an X substituent is attached to the central carbon atom in a chain, symmetry may also be created, for example 3-chloropentane. However, it is worth noting that this only works with a carbon chain containing an uneven number of carbon atoms. As we can see, in 3-chloropentane, the symmetry of the molecule creates three different chemical environments. Here is the carbon-13 NMR spectrum of 3-chloropentane. Using what you have learnt so far, can you identify which peak belongs to which carbon atom? Pause the video and try and work it out. So how did you go? Did you identify that the carbon attached to the chlorine atom corresponds to the peak furthest downfield, highlighted in green? Did you remember that the carbon of a CH3 group is usually furthest upfield? If so, well done. You are getting the hang of carbon-13 NMR interpretation. The following compounds have the same carbon backbone, but the X substituents are located at different positions. Identify the number of different carbon environments in each compound, and therefore the number of peaks in their carbon-13 NMR spectra. In this first example, there are 4 different carbon environments. Notice how the carbon adjacent to the OH group corresponds to the peak furthest downfield on the carbon-13 NMR spectrum, while the CH3 groups remain in the upfield region. The CH3 groups are indistinguishable from each other and therefore are chemically equivalent. In this next example, there are also 4 different carbon environments. The carbon atom adjacent to the substituent, in this case the NH2 group, again corresponds to the peak furthest downfield on the carbon-13 NMR spectrum. And again we see that the carbon atoms of the CH3 groups are furthest upfield, with those of the 3 equivalent CH3 groups slightly downfield of the other CH3 group. In the third example, there are 5 different carbon environments. Placement of the substituent, in this case bromine, on one of the previously chemically equivalent CH3 groups creates a new non-equivalent carbon atom. Before we move on to looking at the carbon-13 NMR spectra of alkenes, let us finish with one more worked example to see how an X substituent can affect the chemical equivalence in a previously symmetrical molecule. As you can see, this molecule, 2-methyl-5-ethylheptane, has 2 areas possessing symmetry, represented by the rectangles. If we add an X atom or substituent, in this case bromine, to the carbon atom at the centre of the symmetry remains. However, if we add the substituent to one of the carbon atoms in the branches, we lose the symmetry and previously equivalent carbon atoms become non-equivalent. If we look at the other section containing symmetry in this molecule, addition of the X substituent, in this case chlorine, at the carbon atom at the center of the symmetry does not affect the number of chemically equivalent carbon atoms. However, attachment of chlorine to any of the carbon atoms in the branches increases the number of chemically non-equivalent carbon atoms. Finally, addition of the X group or substituent to either of the central carbon atoms will have no effect on the number of chemically equivalent carbon atoms. Now let's look at the carbon-13 NMR spectra for alkenes. The peaks for the alkene carbon atoms are fairly easy to identify, as they typically fall between 100 to 150 parts per million. Their exact chemical shift will of course depend on what other groups are also present in the alkene molecule. In this first example, that of 2-hexene, we can see 6 peaks in the carbon-13 NMR spectra, 1 for each carbon atom. This indicates that there is no symmetry within this molecule. 2 of the peaks fall between 100 to 150 parts per million. These are the 2 carbon atoms involved in the carbon-carbon double bond. As we move upfield from these 2 peaks, the next 2 peaks correspond to the 2 CH2 groups, with the last 2 peaks furthest upfield corresponding to the 2 CH3 groups. In our next example, that of pent-4-ene-2-ol, we can see 5 NMR peaks for a molecule containing 5 carbon atoms. Hence there is no symmetry and no chemical equivalence. Starting at the left-hand side or downfield end of the spectra, we first see the 2 carbon atoms involved in the carbon-carbon double bond in the 100 to 150 part per million region. Moving upfield, the next peak at approximately 67 parts per million is that of the carbon adjacent to the OH group. Remember, carbons with substituents such as OH, bromine, chlorine and NH2 tend to appear in the region between 35 to 100 parts per million. The last 2 peaks belong to the remaining CH2 and CH3 groups. As expected, the CH3 group is the furthest upfield. The chemical shift for both of these groups is slightly higher than would be expected in an unsubstituted alkane. This is because of the effect of the nearby OH group, which moves them slightly downfield. When it comes to alkanes, chemically equivalent carbon atoms can be identified by a line of symmetry perpendicular to the carbon-carbon double bond, or by locating a symmetrical 180-degree rotation about the carbon-carbon double bond. Even a minor change to the symmetrical structure will remove the symmetry and therefore the chemical equivalence. For example, change of an ethyl group to a methyl group. Now let's move on to the final group of compounds for this presentation, those containing a carbonyl group. The peak for a carbonyl group appears between 150 and 250 parts per million, with its exact position depending on what type of carbonyl compound it is and on what other groups might be present in the molecule. Let's look at a few examples of carbonyl compounds, beginning with 3-methyl-2-butanone. Looking at the carbon-13 NMR spectrum, we can see 4 peaks for this 5-carbon compound. This indicates that 2 of the carbon atoms will be chemically equivalent. Can you work out which 2 atoms these will be? Assigning the carbon-13 NMR spectrum of 3-methyl-2-butanone, the peak above 200 parts per million belongs to the carbon atom of the carbonyl group. The next peak, with a chemical shift of approximately 40 parts per million, is a carbon of the CH group adjacent to the carbonyl bond. The remaining 2 upfield peaks are the CH3 groups. The 2 CH3 groups on the left-hand side of the molecule are chemically equivalent, and are furthest downfield because they are further away from the carbonyl group. Because the CH3 group on the right hand side of the molecule is adjacent to the carbonyl group, its peak is moved slightly downfield. Our next example is butyl acetate. From what you have learnt so far, do you think you can assign all 6 peaks in this NMR spectrum? Pause the video and see if you can. The downfield peak, just above 170 parts per million, is due to the carbon atom of the carbonyl group. The peak with a chemical shift of 64 parts per million is the CH2 group connected to the oxygen of the ester group. The remaining CH2 groups move further upfield the further they move away from the ester group. The CH3 group at the right hand end of the molecule corresponds to the peak furthest upfield, just above 10 parts per million. The other CH3 group on the left hand end of the molecule occurs further downfield due to the influence of the adjacent carbonyl group. Let us now consider the effect of symmetry in carbonyl compounds. Most carbonyl compounds, for example carboxylic acids, acid chlorides, amides and aldehydes, are only found at the end of carbon chains. Therefore they have no intrinsic symmetry. The ester group itself is asymmetrical, leaving only ketones as able to form symmetrical carbon backbones. The structure of ketones places them in the carbon backbone of organic compounds. So symmetry is straightforward to identify by drawing a line of symmetry through the carbonyl compound. Here is an example of a symmetrical ketone, 2,4-dimethyl-3-pentanone. See if you can identify which peaks correspond to which carbon atoms, and explain why there are only 3 peaks for a compound which contains 7 carbon atoms. Based on what we have learnt so far, you should be able to identify the peak just under 220 parts per million as belonging to the carbon of the carbonyl group. Hopefully you also identified that the 2 chemically equivalent CH groups would be the peak just under 40 parts per million, shown in yellow. Finally, the upfield peak belongs to all 4 CH3 groups, which are chemically equivalent. We have now covered basic interpretation of carbon-13 NMR spectra for simple organic compounds. To summarize, carbon-13 NMR spectra are an important resource for chemists studying organic compounds. The chemical shift of a peak gives an idea about what functional groups are present, while the number of peaks can indicate if there is symmetry within the organic molecule. Finally, skills interpreting carbon-13 NMR spectra only come with practice. If you are interested in looking at more carbon-13 NMR spectra, the spectral database for organic compounds is an excellent resource. This can be readily accessed by going to the address listed below. All of the spectra used in this presentation were obtained from the spectral database.